Welcome to EPG Pathshala. In this module, you will learn the basics of logic gates. Logic gates are the fundamental building blocks of digital electronics. The term logic gates refers to the ability of a device to make the decisions. Based on this, we have three basic types of logic gates. These are AND gate, OR gate and NOT gate. In addition to that, we have two derived gates, NAND and NOR gates. In addition to this, there are two more logic gates. The XOR and XNOR are normally preferred as arithmetic circuits. These are normally used as inequality gates. In addition to this, if we refer to the representation of logic symbols, there are two types of representations preferred in IEEE. The traditional logic symbols are the distinctive shapes, whereas the new logic symbols, those are suggested by ANSI and IEEE, are the rectangular outline symbols. Logic gates basically follows the Boolean algebra. It accepts binary inputs, like it could be 0 or 1, true or false, or it could be high and low. In this module, we will emphasize on the basic operations of logic gates. In this module, you will learn about the basics of logic gates and why are they referred to as fundamental building block of any digital system. The operation of logic gates will be explored using analogy and truth table. In addition, you will understand the concept of universal logic gates, how NAND and NOR gates can be used in constructing other basic logic gates. You will also study how ANSI and IEEE standard symbols for logic gates are different from the distinctive shapes. Another interesting thing you will learn is the pulse or timing operations of the logic gates. In addition, simple applications of logic gates will be explored. Let us now begin the discussion of logic gates. Logic gates can be understood well by understanding the basic learning philosophy. I have 6 good friends. These are 5 W's and 1 H. What, why, when, where, who and how. Through this learning methodology, we will understand the topic completely right from the beginning to the application part. Let us begin the discussion through a simple question. What is a logic gate? A logic gate, as the basic building block of a digital system, is capable of making the decision. It is an electronic circuit with one or many inputs and only one output. Most logic gates have 2 inputs and 1 output. At any given instant, every input or output terminal is one of the 2 logic conditions, true or false, which describes the logic value. 1 or 0 provides binary value. High or low describes the voltage level and on and off describes the switch position. Let us now move on to the second question related to why. Why do we need to study logic gates? It will throw light on importance of the logic gate. Study of logic gates can help you to understand the operation of logic circuit. In addition to that, clear understanding of the operation of logic gates can help you to construct different complex circuit. With the help of the understanding of logic gates, you can analyze the signal flow in the logic circuit. The third question will help you in identifying the applications of the topic. Where do we use logic gates? Logic gates find applications in numerous digital devices and products. Logic gates are used in constructing various logic devices like multiplexers, demultiplexers, code converters, arithmetic and logic unit, where the number of logic gates are between 10 to 1000. They are typically used in microprocessors, microcontrollers, in which over 1 million gates are present in these devices. Every digital electronic gadget, including PC, laptop, tablet PC, mobile phones, calculators, digital watches, LED and LCD TVs are constructed using logic gates. The fourth question will help us in identify the need of the topic. When do we use logic gates? In last decade, there is a shift from analog electronics products to digital electronics. In last couple of decades, the digital revolution has spread to many other aspects of life. Some examples of once analog systems that have now gone digital, like still picture photography, audio video recording, telephone systems, etc. There are many reasons for the shift from analog electronics to digital technology. Some of these reasons are: digital systems provide better accuracy and precision in measurement. As digital devices operate only in two states, on or off, only few basic operations are performed by the digital circuits. No special math skills are required to design. Thus, digital systems are easy to design. There are many logic devices and families available to the designer to introduce flexibility in design. One of the major features of digital system is their programmability. This is possible only because of programmable logic devices. As there are only few operations for the devices, on or off, digital systems provide higher speed of operation. Digital circuits can provide a lot of functionality in a small space, as the circuits are integrated in a single chip and produced on a large scale to provide lower cost. This is the reason why do we use logic gates. The fifth question is related to who will design and build the logic circuit. Obviously, teacher as a mentor and student can act as a logic designer. The last and the most important question is about how. It will require a quite long time to understand how do we do it. The logic gates can be constructed using logic families like TTL, CMOS or ECL. These families are built using basic devices like diodes, transistors, MOSFETs and resistors, etc. In digital systems, there are very few basic operations performed irrespective of the complexities. There are three basic operations in digital systems. It provides three basic logic gates, that is AND, OR and NOT gate. The relationship between the inputs and outputs is based on certain logic. Logic gates basically perform some basic logic functions. The basic logic functions are ANDing, ORing and inversion. Let us now discuss these logic gates. The NOT gate is popularly known as inverter. It performs logical inversion or complementation. The purpose of inverter is to change one logic level to opposite level. The low level at the input produces a high level and vice versa. In terms of bits, it changes a 0 to a 1 and a 1 to 0. Let us now consider an electronic circuit consisting of battery, resistor, switch and lamp to implement simple NOT gate or inverter. The open switch is corresponding to logic 0, turns the lamp on indicating logic 1. The closed switch corresponds to logic 1, turns the lamp off indicating logic 0. Thus, the NOT gate inverts or complements the input. NOT gate provides logical inversion. Let us now talk about AND gate. The AND gate performs logical multiplication or AND function. When both the inputs are at logic 0, the output of AND gate is 0. Let us now consider an electronic circuit consisting of battery, resistor, switches and lamp to explain AND function. When both the switches are open, that is at 0 level, no current flows from battery to lamp, thus the lamp is off. When one of the inputs is at logic 0 and other one is at logic 1, still the output of AND gate is 0. Referring to the switch analogy, when one of the switches is open, that is at 0 level, and the other one is closed, that is at logic 1, then the lamp is off. As the circuit is not complete, there is no current flowing from battery to the lamp, thereby keeping the lamp off. Thus, if any one or both the inputs are at logic 0, then AND gate produces logic 0. Referring to the switch analogy, when any one or both the switches are open, that is at 0 level, the circuit is not complete. Therefore, no current flows from battery to lamp, thus the lamp is off. When both inputs of the AND gate are at logic 1, then the output is at logic 1. Referring to the switch analogy, both switches are closed, that is at logic 1. The circuit is complete, therefore, current flows from battery to the lamp, which in turn makes the lamp on. Just to sum up, the AND gate produces a logic 1 if and only if all the inputs are at logic 1. Let us now discuss the operation of OR gate. The OR gate performs logical addition. An OR gate has 2 or more inputs and 1 output. When both the inputs are at logic 0, that is low, the output of OR gate is also low. Let us now consider an electronic circuit consisting of battery, resistor, switches and lamp to explain the OR gate function. When both the switches are open, that is at level 0, no current flows from battery to lamp, thus lamp is off. When one of the input is at logic 0 and the other one is at logic 1, then the output of OR gate is 1. Referring to the switch analogy, when one of the switches is closed, that is at level 1 and other one is open at 0 level, the lamp is on, indicating logic 1. As the circuit is complete, the current flows from battery to lamp, thereby turning the lamp on. Similarly, when one of the input is at logic 1 and other input is at logic 0, then the output of OR gate is 1. Referring back to the switch analogy, when one of the switches is closed, that is at one level, and the other one is open, then the lamp is on, indicating logic 1. As the circuit is complete, the current flows from battery to lamp, thereby turning the lamp on. When both inputs of OR gate are at logic 1, then the output is at logic 1, that is high. Referring to the switch analogy, when both the switches are closed, that is at one level, the circuit is complete. Therefore, current flows from battery to lamp, which is in turn makes the lamp on, and an OR gate produces a high output if any of its inputs are at logic high. Let us now study NAND gate, that is not AND gate. It basically performs logical ANDing and then provides inverted or complemented output. Let us now study the logical operation of NAND gate. The NAND gate produces a high output when both the inputs are low. In the NAND gate circuit constructed using switch analogy, the switches are in parallel with the battery and lamp. The lamp is on when both the switches are open. NAND gate produces a high output when any of the inputs are low. The lamp is on when any of the switches open. The NAND gate produces a high output when any of the inputs either A or B or both are low. The lamp is on with a condition either A or a B or both switches are open. NAND gate produces a low output when both the inputs are at high level. The lamp is off when both the switches are closed. NOR gate is basically a NOT OR gate. It performs logical ORing and then provides inverted or complemented output. Let us now study the logical operation of the NOR gate. NOR gate produces a high output when both the inputs are low. In the NOR gate circuit constructed using switch analogy, the individual switch is in parallel with the battery and the lamp. The lamp is on when both the switches are open. NOR gate produces a low output when any of its inputs are high. The lamp is off when any of the switch is closed. The NOR gate produces a low output when any of the inputs either A or B is low. The lamp is off when any of these input switches are closed. NOR gate produces a low output when any of the inputs either A or B or both are at logic 1. The lamp is off either A or B or both switches are closed. Let us now study the truth table of XOR gate, that is exclusive OR gate. This gate basically designed to exclude the condition of standard OR gate to generate real binary addition. The output of XOR gate is low when both the inputs are low. In the switch analogy, XOR gate is constructed using battery, lamp, resistor and cross connected switches. The lamp is off when both the switches are open. The output of XOR gate is high when one of the input is high. The lamp is on when one of the switches is closed. The output of XOR gate is high when any one of the input is high. The lamp is on when any of the switch is closed. The output of XOR gate is low when both the inputs are high. The lamp is off when both the switches are closed. This is in turn indicates that XOR gate produces a logic high only when the two inputs are at opposite levels. Let us now study the truth table of XNOR gate, that is exclusive NOR gate. This gate basically is designed to compare the two inputs. The output of XNOR gate is high when both the inputs are low. In the switch analogy, XNOR gate can be constructed using a battery, lamp, resistor and cross connected switches. The lamp is on when both the switches are open. The output of XNOR gate is low when one of the input is high. The lamp is off when one of the switches is closed. The output of XNOR gate is low when any one of the input is high. The lamp is off when any of the switch is closed. The output of XNOR gate is high when both the inputs are high. The lamp is on when both the switches are closed. This in turn indicates that XNOR gate produces a high output only when two inputs are at the same logic level. Let us now study IEEE and ANSI standard symbols for representation of logic gates. The logic symbols we have used so far are traditional distinctive shape symbols for the logic gates. A new standard for logic symbols was suggested by IEEE ANSI in the year 1984. These symbols are rectangular outline symbols for all logic gates. American National Standards Institute, that is ANSI, and Institute of Electrical and Electronics Engineers IEEE has recognized both distinctive shapes and rectangular outline symbols for the logic gates. Rectangular outline symbols are preferred while representing the complex logic circuits. The rectangular symbols use a polarity indicator, that is a small right triangle in place of small bubble in the traditional symbol to indicate inversion of the logic level. The presence and absence of polarity indicator indicate whether an input or output is active low or active high. In addition, a special notation inside each rectangular outline describes the logic relation between inputs and output. The number 1 inside the inverter symbol indicates a device has only one input, and the polarity indicator at output indicates that output is active low. The AND symbol inside the rectangular shape indicates the AND gate symbol, and output will be active high state when both the inputs are in active high state. The greater than or equal to symbol inside the rectangular shape indicates OR gate symbol, and output will go in active high state when one or more inputs are in active high state. The rectangular symbol for NAND and NOR gates are the same as the AND and OR gate respectively, with the addition of polarity indicator on the output. This indicates the outputs are in active low states. XOR and XNOR gates are having equal to 1 symbol in the rectangular outline indicates one and only one input must be active to activate the output. Let us now explore the logic gates with more than 2 inputs, that is multiple input logic gates. Majority of the logic gates discussed so far were having only 2 inputs. What happens when multiple inputs are present for the logic gate? With the input variable A, B, C, D, etc., the output of this AND gate is equal to A and B and C and D, etc. Let us consider 4 input AND gate. With 4 inputs, the number of possible combinations at the input would be 2 to the power 4, that is 16 possible combinations of zeros and ones in the truth table. In case of this AND gate, the output Y is at logic 1 if and only if all inputs are at logic 1. For all other conditions, the output is at logic 0. Let us explore the multiple input OR gate. With the input variables A, B, C and D, the output of OR gate is equal to A or B or C or D. Let us consider 4 input OR gate. With 4 inputs, the number of possible combinations at the input would be 2 to the power 4, that is 16 possible combinations of zeros and ones at the input. In case of this OR gate, the output of Y is at logic 1 if any one of the input or all inputs are at logic 1, else the output is at logic 0. Let us now study how NAND and NOR gates can be used as universal logic gates. Any digital circuit can be realized by using 3 basic logic gates AND, OR and NOT gates. Let us now consider the importance of NAND and NOR logic gates. The NAND and NOR gates are preferred as universal logic gates, as each of these gates can be used to construct basic logic gates AND, OR and NOT gates. Let us consider now NAND gate as a universal logic gate. Let us now construct NOT gate using NAND gate. A NAND gate can be used to construct NOT gate by connecting all its inputs together and applying input to a common terminal. The output of NAND gate generates the output as NOT A. Let us now consider the construction of AND gate using NAND gates. The construction indicates we require 2 NAND gates. The first NAND gate provides complement of A and B, whereas the second NAND gate acts like as an inverter. Double complement will cancel each other to provide AND gate. The derivation of Boolean expression will be discussed later in the Boolean expression module. 3 NAND gates are required to construct the OR gate. The first level 2 NAND gates will act like an inverter. These 2 inverters will complement the inputs. The third NAND gate will perform ANDing of complemented inputs. Then it inverts the results. This provides final output as a logical OR function. The derivation of this logic gate will be discussed in the Boolean algebra. Let us now consider NOR gate as a universal logic gate. Let us now construct NOT gate using NOR gate. A NOR gate can be used as NOT gate by connecting all its inputs together and applying input to the common terminal. The output of NOR gate generates output as NOT A, that is complement of A. Let us now construct AND gate using NOR gate. The construction indicates we require 2 NOR gates. The first NOR gate provides complement of A or B, whereas the second NOR gate acts like an inverter. The double complement will cancel each other to provide action of the OR gate. 3 NOR gates are required to construct OR gate. In the first level, 2 NOR gates will act like an inverter. These 2 inverters will complement the inputs. The third NOR gate will perform ORing of the complemented inputs first and then inverts the result. This provides final output as logical AND function. Let us now study different possible gates. The open collector outputs of several NAND gates can be connected together to form the wired AND function. In this example, 3 open collector NAND gate outputs are wired together as shown in the figure. One single pull-up resistor is sufficient for this interconnection. The output Y of the circuit configuration is the ANDing of all the inputs. The equation for output Y is complement of A and B and complement of C and D and complement of E and F. The open collector outputs of several NOT gates can also be connected together to form the wired AND gate. In this example, 3 open collector NOT gate outputs are wired together as shown in this figure. One single pull-up resistor is sufficient for this interconnection. The output of the logic gate, that is Y, is the ANDing of all the inputs. Let us now discuss the tri-state logic gates. Tri-state logic gates are most important logic gates in interfacing various devices and bus. Tri-state logic gates have 3 possible output states, namely logic 1 state, the logic 0 state and a high impedance state. The high impedance state is controlled by an external enable input. The enable input decides whether the gate is active or in the high impedance state. When active, it can be either in 0 or 1 depending upon the input conditions. In this gate, when enable input is high, NAND function provides 0 or 1 depending on the input conditions. If enable is low, the NAND gate output will provide high impedance state independent of the input combinations. Let us now consider NAND gate with active low enable input. The high impedance state is controlled by the external enable. The enable input decides whether the gate is active or in high impedance state. In this gate, when enable input is low, the NAND function provides 0 or 1 depending upon the input combination. If enable is high, the NAND gate output will provide high impedance state independent of the input combinations. Let us consider the interconnection of tri-state inverters together to form a common bus. When tri-state devices are paralleled, only one of them is enabled at a time. High enable input activates the respective NOT gate and with a condition that only one of them is enabled at a time. Let us now consider a different logic gates as compared to the traditional logic gates. It is popularly known as Schmidt gate. All standard logic gates have single input threshold voltage level. This threshold is the same for both low to high and high to low output transitions. These gates provide erratic output for slowly changing input. A novel solution to this problem is to have 2 different threshold voltage levels, one for low to high transition and the other for high to low transition. By introducing some positive feedback in the internal gate circuitry, a phenomena called hysteresis will be present in this logic gate. Here we are considering NAND and NOT gate with built-in hysteresis. These gates are referred to as Schmidt gates. This gate interprets slowly changing input voltages according to 2 threshold voltages. Lower and upper threshold voltages are normally used for low to high and high to low transitions respectively. Hysteresis increases noise immunity of the digital system. A tri-state buffer is a device that allows you to control an output signal transferred to the bus. When tri-state buffer's enable bit is active, the input of the device transfers the data to the output. When it is inactive, the output of the device is in tri-state. A buffer is a logic gate with output same as input level. A tri-state buffer is a useful device that allows us to control when current passes through the device and when it does not. A tri-state buffer has two inputs, a data input A and a enable input E. When enable input is active, that is at logic 1, then the output is same as input. If enable input is 0, then the output is in tri-state. In many applications, we need tri-state buffers with active low enable input. A transceiver is a bidirectional buffer with additional direction control and enable pin. It allows flow of data in both the directions depending upon the logic status of the control input. Transceivers like buffers are tri-state devices to make them compatible with bus oriented system. When active high input is provided at enable input E1, then data is transferred from A to B in a complemented form. When the enable input E2 is at logic 1, then data is transferred from B to A in the complemented form. Let us consider the example of buffers as transceivers. When active high enable input is provided at E1, it transfers the data from A to B without complementation, whereas when the enable input E2 is 1, then the data is transferred from B to A. Let us now talk about a special arrangement of the gate called as AOI gates. This special arrangement of 3 logic gates is known as AOI gate, that is AND or invert gate. It is used in many applications of combinational systems. In many applications, the input to a gate are not stationary, but changing dynamically between two voltage levels frequently. This type of changing voltage or logic levels give rise to pulse waveform. Let us now study the response of different logic gates with pulse input waveform. Let us now study the response of NOT gate to the pulse input waveform. It is important to note that the logic gates obey the truth table irrespective of the static or dynamic inputs. For a NOT gate, if input is at logic 0, then the output will be 1 and vice versa. The output is inverted as compared to the input. Let us now study the pulse response of AND gate. In order to study the pulse response, it is important to look at the input of the gate with respect to each other to determine the output level at any time. Let us consider two AND gates with one of the input is fixed and tied to either 0 or 1, and pulse waveform is applied to the other input. Initially, when we apply square wave to the input of AND gate with other inputs are tied to 1 or 0, it is observed that when one of the input is at logic 1, the same output waveform is generated at the output of AND gate. So, the output is high only when both the inputs are high. Therefore, the AND gate with high input provides enable gate, whereas the other gate where the input is tied to 0 is referred as inhibit gate, which stops the input square wave reaching to the output. Let us now consider the pulse operation of OR gate. Just similar to AND gate, we will be connecting one of the input of OR gate to logic 0 and the other logic gate will receive logic 1 at the input, and square wave is applied simultaneously to both the logic gates to determine whether the input signal is passed as it is to the output or it is stopped. As it is seen from the waveform, the OR gate with one of the input at logic 0 transfers the input waveform at the other input to the output, and when the OR gate receives logic 1 at one of the input, by default the waveform is blocked, is not allowed to pass, and the output is at logic 1. Thus, we can comment the output of OR gate is high only when either or both the inputs are high. Let us now talk about the pulse operation with NAND gate. Just similar to the previous logic gates, let us apply logic 1 to the first NAND gate and logic 0 to the second NAND gate. The input that is applied to both the NAND gates is square wave. It is observed that the gate which has one of the input as logic 1, it allows the waveform to be passed, but it is in a complemented form. Thus, the first NAND gate acts like an enable gate, whereas when one of the input is low, then the square wave does not reach at the output. Therefore, when the output is low, only when both the inputs are at logic high. Let us now move on to the pulse operation of NOR gate. In this case, one of the NOR gate receives logic 0 as the input and the other gate receives logic 1 at the input. After the application of square wave, it is observed that the NOR gate with one of the input as 0 transfers the square wave to the output, but in a complemented form. Therefore, this logic gates acts like an enable gate, whereas the NOR gate with one of the input at logic 1 acts like an inhibit gate, thereby blocking the square wave reaching to the output. Now, let us study simple applications of logic gates. There are many applications wherein we can use logic gates. To start with, let us consider very simple applications. The first application is of safety lock. Simple AND and NOT gates are used in safety lock application. Switches are used as inputs to the logic gates. First AND gate drives the solenoid based lock. Switch A corresponds to banker's key and switch B corresponds to customer's key. To open the lock, the solenoid must be activated. To open the lock, both the keys must be inserted, that is, switch A and switch B must be pressed simultaneously. If B is pressed before A, then the buzzer will be turned on to generate the sound. Let us now consider another application of logic gates, freezer warning buzzer. When the thermistor is cold, its resistance is high and the input of NAND gate is also high. Since the NAND gate is connected as an inverter, the output is low. As the thermistor warms up, its resistance decreases and voltage across it falls, and the input to the NAND gate falls. When it becomes low enough, the output becomes high and the buzzer generates sound. Let us now consider another application of enable gate for counter. AND gate is popularly used as enable gate or inhibit gate. Enable gate allows the input data to pass through it to the output, whereas the inhibit gate provides just reverse process of enable gate, that is, this allows the data through the gate to the output. Let us now consider an application of AND gate in frequency counter. For measurement of frequency, a gating pulse of known frequency is applied to one of the input of AND gate, and unknown clock frequency is connected to the other terminal. When the gating pulse is high, the clock frequency is passed to the counter, which in turn measures the number of pulses in the known duration. Let us consider another example of industrial plant control. Let us consider the application of Schmitt gate. Schmitt inverters are popularly used as oscillators. A simple circuit containing R and C is shown here. This oscillator produces a square wave output waveform. Let us consider initially the capacitor C is fully charged, so that the input of the inverter is low, producing an inverted output which is high. The output of the inverter is fed back to the input through a resistor R. The capacitor starts charging in this process. When the capacitor charges to upper threshold limit of Schmitt inverter, the inverter changes the state and the output becomes low. This condition initiates the discharge process of the capacitor through the resistor. Discharging process continues until the capacitor voltage reaches the lower threshold level, where the inverter changes the state again. This switching back and forth by the inverter produces a square wave with a frequency of f is equal to 680 upon R into C. Let us now consider last application in this module. This application is of NAND gate, which is popularly used in burglar alarm system. In addition to the NAND gate IC, LDR, push button switch and a buzzer are required in the application. The light dependent resistor, that is LDR, detects change in light intensity. When the LDR is in the light, the one input of NAND gate is low. Similarly, when the switch is closed, the other input of NAND gate is low. Thus, either the switch is closed or the light on one of the input is low, the output is high and the buzzer produces an alarm. Let us now summarize the topics that we have studied so far. Logic gates are the basic building blocks of the digital systems and all gadgets. NOT gate inverts the input. The AND gate produces output high only when all the inputs are 1. OR gate produces high output if one or more than one inputs are high. NAND gate produces active low output if both the inputs are at logic high. NOR gate will provide output low only when one or many inputs are at logic high. XOR gate output is high when the inputs are not the same. XNOR gate output is low when inputs are not the same. NAND and NOR gates are called as universal logic gate. IEEE and ANSI supports traditional distinctive shapes as well as rectangular outline symbols for the logic gates. Logic gates can be used in two basic applications, enable gate and inhibit gate. Logic gates are used in many household and industrial applications as well.